Hello everyone. So I hope that you are doing good today. So today, here in Advanced Engineering Mathematics for Civil Engineers, we're going to continue our discussion about complex numbers. So this will be the part 2. Okay, so for this topic, we will have the same intended learning outcome. So students must be able to evaluate complex number of various forms, functions, and operations. So let's start the discussion. Okay, so let's talk about now the Moivre's theorem. So what does this theorem state? Okay, so this says to raise a complex number to a power, raise the modulus to that power, and multiply the argument by that power. So this theorem is actually applicable for a power of complex numbers and solving for the roots of complex numbers. So let's say you have here this complex number. So this complex number is in a form wherein there is a modulus, okay, and there is an argument. So that's what we need, okay, in order for us to apply the Moivre's theorem. Your complex number should have modulus and argument. So what are the forms of complex numbers that have modulus and argument? So those are trigonometric functions, polar functions, and even exponential form rather, no, not function. So I'll repeat: trigonometric form, polar form, and exponential form. So that's the form that we need here in the Moivre's theorem to apply the Moivre's theorem. Okay, so let's say if we have here a complex number, okay, and it is raised to a certain power. Okay, so let's say that power is let's say raised to the fifth power, sixth power, or even to the 20th power. Okay, so if that's the case, okay, it will be to solve this manually, this complex number manually. Okay, it will be a long solution. So instead of solving this manually, we're going to use this theorem, okay, to solve for a complex number that is raised to a certain or to a specific power. Okay, so if a complex number is raised to a specific power, okay, so what we're going to do here, as mentioned in this theorem, so we have to raise the modulus. So our modulus is r, so we just have to raise our modulus r to that power. So that will be r raised to n. So this will be that value, r raised to n, and then multiply the argument by that power. So in this case, the arguments here are this theta, right? So we're just going to multiply our power. Our power is n, okay? And we're just going to multiply that to all our arguments. So that will be n theta plus I sine n theta. So we just multiply the argument by that power. Okay, so that's the rule for applying this first proposition, no, for power of the Moivre's theorem. Okay, wherein your n should be greater than or equal to 1. Okay, so it should be also a positive integer, your n or your power here. Okay, so that's how you solve the power of a complex number using the Moivre's theorem. Now, to solve for the roots of a complex number, okay, so let's say again we have here we have here a complex number and it is raised to a fraction, okay, to a exponent that is fraction. So what we're going to do here is find the roots, okay, of the complex number. Okay, so this is raised to an exponent or a power that is fraction, right? So your denominator here will be n. Okay, so again, the form of complex number that we need here, it should have r and theta. So it should either be a trigonometric form, polar form, or exponential form. But in this case, we use trigonometric form. Okay, so again, the rule here is the same. We have to raise the modulus to that power. So we just have to raise r to its power, which is 1 over n. So that will be r raised to 1 over n. And then we just have to multiply, okay, the argument by that power. So our power here is 1 over n. So we're just going to multiply our theta, okay, by 1 over n. But in this case, this is a little different from what we have done here in the power, right? So instead of just multiplying your theta, okay, by the power, which is a fraction. Okay, so we will add here 2 pi k. Okay, so for solving the roots. Okay, so it's a little different nga from your power. Okay, so we will add here plus 2 pi k. Okay, also here plus 2 pi k, where in your k, it will be from 0 to n minus 1. Okay, so meaning to say, okay, so your values, okay, the values that you're going to get, okay, or the values of the roots that you're going to get here will depend on your n. Okay, so let example, your n, the value of your n, let's say is 5. Okay, so the values of your k will be from 0 to 5 minus 1. Meaning to say, 5 minus 1 is 4. So your values for the roots for that problem, if your n here is 5, so your k should be 0, from 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. So you will have 5 values for your roots, okay, for solving the roots of complex numbers. Okay, so let's start solving this problem. Okay, let's proceed. So let's simplify the following example. So for the first example, we have to simplify this complex number. Z is equal to negative square root of 3 plus I raised to the fourth power. So in this case, class, we can actually solve this manually. We can multiply negative square root of 3 plus I times negative square root of 3 plus I. And then after you answer that, you multiply it again by negative square root of 3 plus I. And then after you get the answer, you will again multiply by negative square root of 3 plus I. So you're going to multiply that 4 times, okay, to get the fourth power. So that's how you solve it manually. But it will be a long solution, right? So for this, we're going to use, okay, the concept of the Moivre's theorem. Okay, so we're going to solve this using the Moivre's theorem. But the thing here is that before we can apply or use the Moivre's theorem for our complex number raised to the fourth power, we have to convert first our complex number into a form wherein there is a r, okay, or modulus, and there's a theta or argument. Okay, so we have to convert this rectangular form into either polar form, trigonometric form, or exponential form. So in this case, okay, we're going we have to determine first the r and theta. Okay, so for complex number negative z or negative square root of 3 plus I, okay, its r will just be square root of negative 3 squared plus 1 squared, right? So that will be the value for your r, okay? And that value will be equal to positive 2, okay, or 2, no? So that will be your r. Now for your theta, so again, before solving your theta, you have to consider first, okay, the quadrant where your complex number is located. So in this case, this negative square root of 3 plus I, it is actually located in your second quadrant. Tama ba? It's located in the second quadrant because the x-coordinate is negative and the y-coordinate is positive. So therefore, it is in second quadrant. So for solving for argument in the second quadrant, okay, that's just arctangent of y over x. Your y is 1 over your x, which is negative square root of 3 plus pi, right? That's how you solve arguments, okay, of complex numbers located in the second quadrant. And that will give you 5 pi over 6 radians. So this will be the r and theta. Okay, so from this r and theta, okay, we can now convert, okay, our complex number in rectangular form to this is in polar form, right? So we converted this to polar form. Okay, so your r is 2 angle and your theta or argument is 5 pi over 6. So this will now be the equivalent, okay, of this complex number, and this is raised to the fourth power. Okay, so from that, we're going to apply De Moivre's theorem. Okay, so it was mentioned in the De Moivre's theorem that what you're going to do here is just raise your r or your modulus to the power or to the given power, and that is 4. So this will just become 2 to the fourth power, and your angle, okay, it should just be multiplied, okay, by the theta or your argument, okay. So that will be 4 times 5 pi over 6. So simplifying this will give you 16 angle of 10 over 3 pi. So this will now be the answer. So that's just how you solve, okay, for the power, okay, of this complex number. So in this case, it was not mentioned in the problem, okay. So what should be your final answer? So this can be your final answer. But if it is mentioned in the problem that you have to convert your final answer to rectangular form or trigonometric form or any form, so you have to convert this. But since there's no such instruction mentioned in the problem, so this will now be your answer. So this is 16 angle of 10 over 3 pi. So that will be the answer. Now, let's proceed to sample problem number 2. So here in sample problem number 2, so in the next slide, let's discuss this. Okay, so this will be the second problem. So this is z to the fifth is equal to 1,121 minus 404i. So in this case, we're going to solve for the roots. Okay, we're going to solve for the roots of this complex number. So we're going to, we have to multiply both sides, okay, by 1/5, okay, to cancel this fifth power here, okay, so that what we're going to solve here is z. Okay, so that will be z is equal to 1,121 minus 404i raised to 1/5, right? So this will be now the given. So here, okay, so your n here will be 5, right? So meaning to say, your the roots, okay, the values of the roots that we're going to solve here are 0 from k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. So there will be 5 roots, okay, for this problem. Okay, so again, before we can apply the Moivre's theorem, okay, we need first to convert this rectangular form of complex number into a form, okay, into a complex number form that has r or modulus and has argument or theta. So let's first solve for r. So for the value of your modulus or r, that will just be equal to square root of 1,121 squared plus negative 404 squared. And that will give you 1,191.57753. Okay, and your theta, again, before solving for theta, you have to consider the location of quadrant of your complex number. So for your complex number, with this complex number, it is located in the fourth quadrant, right? Since it has positive x coordinate and negative y coordinate. So it is located in the fourth quadrant. So for solving the argument of that complex number, okay, located in the fourth quadrant, that will just be simply equal to arctangent of your y over x, wherein your y is the imaginary part, so that will be negative 404 over your real part, which is 1121. So that will give you negative 0.34590 radian. So that will be your theta. So substituting that, okay, to your polar form, so that will be 1191.57753 angle of negative 0.3. So this is the polar form of of our original given in rectangular form. Okay, so this will be its equivalent polar form, and this is raised to 1/5. Okay, so now again, applying the Moivre's theorem, okay, so what we're going to do here is just raise, okay, your modulus r, okay, to the power. So that will be 1191.57753, and your power is 1/5. So that will be raised to 1/5. And what you're going to do is multiply your argument by that power. But in this case, this will be a little different from solving powers from your first example. So we will add here plus 2 pi k. Okay, so that will be the product of the of your power and your angle theta plus 2 pi k. Okay, where in your k, it will be from 0 up to n minus 1. In this case, our n here is 5. So that will be 5 minus 1. So that will be 4. Okay, so your values for k will be k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, and k is equal to 4. So there will be 5 values of roots, okay, for this problem. So this will become our working formula. No? So we're just going to substitute values of k here. Okay, so for k is equal to 0, okay, so if we substitute k is equal to 0, so what will happen here is that 1191.57753 raised to 1/5, that will be equal to 4.12311 angle of negative 0. Where's my calculator? Okay, so angle of negative 0.06918. So let's try to input this in our calculator. No? So again, that is 1191.57753 raised to 1/5. So raised to 1/5. So that will really be equal to 4.12311. Okay, now for 1/5 times negative 0.34590, okay, plus 2 pi times 0. So that will just be cancelled. This will just be cancelled. So that will just be 1/5 times negative 0.34590. So that will give you negative 0.06918. So this will be the answer for if your k is equal to 0. Now, if your k is equal to 1, we just substitute 1 here in this k. Okay, so again, 1191.57753 raised to 1/5. So that will just be the same, 4.12311. And here, this will be 1/5. Okay, so that will be 1/5 times negative 0.34590 plus 2 pi, and your k will be 1. So substitute 1 to k. So it will give you 1.18746. So this is right. So that will be the answer if k is equal to 1. Now, if k is equal to 2, okay, so that will be 1191.57753 raised to 1/5. So it will be the same, 4.12311. Now, for your angle, 1/5 times 0.34590 plus 2 pi times 2. So just change the 1 here, okay, to 2. So change it as 2. Okay, so your angle will be 2.4409. So this will be the answer for this root. Now for the next root, so that will be k is equal to 3. So again, 1191.57753 raised to 1/5, it will just be 4.12311 angle. Okay, so your angle, just change your k here to 3. Okay, so that will be 3.773. Okay, so that will be the answer for this. Now, for the last root, okay, so for our last root, so again, it will be the same. So it will be 4.12311 angle of, so change your k to 4. Okay, so that will be 4.95737. Okay, so that will be the last root. Okay, so if the problem if the question in the problem is this, find the roots of z to the fifth equal to 1121 minus 404i. So automatic that you have to give all the values of the roots. So you have to give these 5 values. Okay, and also if in the problem it's not mentioned, okay, if your final answer, or if it was not mentioned in your problem, the form of your final answer, okay, so this can be can be already, okay, so this can be the answers already, okay, since it's not mentioned nga if what should be the final answer. Okay, so these are the answers for this problem. So let's proceed to the next problem. Okay, so let's talk about now the equality of complex numbers. So for equality of complex numbers, we're going to use this theorem. Okay, a plus bi is equal to c plus di. So meaning to say, the real part at the left side of the equation should be equal to the real part at the right side. Okay, and the imaginary part at the left side of the equation, it should be equal to the imaginary part at the right side of the equation. So to simply put, okay, so your imaginary part a in the left, or real part rather, if your real part here, okay, at your left side, it will just be equal to the real part at the right, which is C. So that will be A is equal to C. And your imaginary part B here, at the left side, okay, it will just be equal to the imaginary part D, okay, at the right side. So that will just be B is equal to D. So that's how equality of complex numbers works. Okay, so let's try to solve some problems about this topic. Okay, so we have to find the value of x and y. Okay, for number 1, x plus I y is equal to 6 minus 4i. So, solving this, okay, using the concept of equality of complex numbers. So, we have here a complex number at the left, and we have a complex number here at the right. So, we can apply equality of complex numbers. So, the real part, okay, at the left side, which is x, it will just be equal to the real part at the right side of the equation. So that will just be x equal to 6. So that will be the value of x. Okay, so that's the item that we are looking for in this problem. And for iy, okay, or for your imaginary part, okay, your imaginary part at the left is y, and your imaginary part at the right is negative 4. So that will be your y. Y is equal to negative 4. Okay, so this will be the answers for number 1. These are the values of x and y. Now, for number 2, okay, so again, your real part here at the left side is 3x, and your real part at the right side is 9. So that will just be 3x equal to 9. So solving for x, so just divide both sides by 3. Okay, so that will be x equal to 3. Now, for your real imaginary part, okay, so that will be 2y is equal to 6. Okay, so this will be that, okay, 2y is equal to 6, and solving for y, divide both sides by 2, so that will just be y is equal to 3. So this will be the answer for number 2. Now, for number 3, this will be a little bit complicated, okay, compared to your number 1 and number 2. So let's solve number 3. Okay, so for your number 3, okay, so this is the given. This is sine to the fourth power x plus cosine squared x sine squared x plus secant squared y over cotangent y minus tangent cube y quantity I is equal to 1/2 plus square root of 3i. Okay, so again, applying equality of complex numbers. So the complex number in the left side is just equal to the complex number at the right side. Okay, so we first have to simplify, okay, this left side, okay, for us to see, okay, the for us to equate it, okay, at the right side, okay, so that our equation will be simple, okay, and simplified. Okay, so simplifying the left side, okay, so we can actually analyzing this, we can actually factor out sine squared x, right? So we can factor out sine squared x from here and sine squared x from here. So factoring that out, so that will be this will now become sine squared x plus this will become cosine squared x. Okay, so from that, okay, we can also simplify this term. Okay, so your secant squared y, as you know from your identities, okay, that your secant squared y, that is also equal to 1 over cosine squared x from here, right? So that will be 1 over cosine squared y over your cotangent y. Its equivalent is this. So that will be cosine y over sine y. So this will be that. Okay, so now for your tangent cube y, okay, we can also apply this. Okay, so this will be sine cube y over cosine cube y. Okay, so just rewrite this remaining terms, okay? And after that, we can simplify this further. Okay, as we know, your sine squared x plus cosine squared x, it's actually one of your Pythagorean identities, right? And you know that that is just equal to 1. Right? So that will just be equal to 1. And then simplifying this, so dividing this two fractions, so that will just be 1 times sine y over cosine squared y times cosine y. So that will be sine y over cosine cube y minus this fraction. So that will just be rewritten here. And then you just rewrite the remaining terms here. Okay, so from here, okay, so we can simplify this further. Okay, we know that this will just become sine squared x times 1, and this can be put into a single fraction, right, by getting the common denominator. So the common denominator is cosine cube y. Okay, so this will become sine y minus sine cube y I. Okay, so just rewrite the remaining terms here. Okay, and from that, okay, we can actually, from here, we can actually factor out sine y, right? So factoring out sine y, so that this will become 1 minus, this will become sine squared y, over, okay, over cosine cube y. Okay, so from here, we can also see this. We can notice this, that this 1 minus sine squared y is actually also from your Pythagorean identity, right? That your 1 minus sine squared x, that is equal to cosine squared x. Okay, so this 1 minus sine squared y will be equal to cosine squared y. Okay, so we can rewrite it this way. Okay, so from here, we can actually cancel out cosine squared y, and there will only be cosine y remaining here, right? Your cosine squared y here in your denominator will be cancelled. So what will remain is just cosine y. So rewriting that again, so what will remain here is cosine y. And again, your sine y over cosine y from your identity, so that is equal to tangent y. Okay, so your sine y over cosine y is equal to tangent y. So rewriting this, so this will now be the simplified form, okay, of our equality here. Okay, so from here, okay, we can now equate the real part in at the left side to the real part at the right side. So the real part here is sine squared x, and the real part here at the right is 1/2. So we can equate that now. So that will be sine squared x equal to 1/2. So to solve for the value of x here, so let's first square root both sides so that we can cancel this square here. So that will be square root of 1/2. And then after that, okay, this will now become sine x equal to square root of 1/2. And to solve for x, we just arc sine. Okay, we just solve for the arc sine of square root of 1/2. Okay, so the value of x will now be arc sine of square root of 1/2. So solving for this, okay, so inputting this in your calculator, that will be arc sine of square root of 1/2. So that will be 1/4 pi. Okay, so that will be 1/4 pi radian. So this will now be the answer for the value of x. Now for the value of y, we just equate the real part at the left side to the real part at the right side. So this will be tangent y is equal to square root of 3. So solving for the value of y, okay, we just solve for the arctangent of square root of 3. So that will be inputting that in your calculator, arctangent of square root of 3. So that will be 1/3 pi. Okay, so this will now be the answer for y. That will be 1/3 pi radian. Okay, so this will now be the values for x and y. So these are the answers now. Now let's proceed to the next topic. So this is a complex number raised to the power of a complex number. So here, okay, your complex number z1, okay, it will be raised to a complex number z2. So if this is the problem, okay, what we're going to do here is, the first one is we have to convert first the complex number to exponential form. So this complex number z1, we will convert it first to exponential form. So that's our rule here. Okay, and the next step will be we have to convert the power to rectangular form. So this power, okay, so which is also a complex number, we will convert this to a rectangular form. So from that, we can start simplifying the given complex number raised to the power of a complex number. Okay, so let's start solving problems, okay, about this topic. So this will be our first example. Okay, so or these are our examples. So number one, we have to simplify z1 raised to z2. Where in your z1, it is equal to 2 plus 3i, and your z2 is equal to 5 angle of pi over 3. So our rule here, okay, for our solution, let's first substitute the values of z1 and z2, no? So your complex number z1 is 2 plus 3i, and your complex number z2 is 5 angle of pi over 3. So from here, okay, so from here, we're going to follow our steps for this type of problem. So our first step, we have to convert this complex number, this 2 plus 3i, into exponential form. So that's our rule. Okay, so to convert this, okay, so we have to solve for the value of r and for the value of theta. So here in this problem, I will no longer show you how to solve r and theta. Okay, so supposedly, if you are already in this point, you already know how to solve r and theta. So for the r of this complex number, so its r is square root of 13. Okay, and your theta will be 0.98279. Okay, so this will now be the exponential form, okay, of this rectangular form. And also our next step, okay, our rule, we have to convert this power, which is also a complex number. Okay, we will convert this into rectangular form. So to convert this into rectangular form, okay, so this will be its rectangular form. So we have to solve for x and y here, right, for the real part and the imaginary part of this complex number. So just in case that you have forgotten how to convert a polar form into a rectangular form, so you just have to solve the real part. So your real part x, okay, it will just be equal to r, okay, cosine of theta, which is pi over 3. So that will be 5 cosine of pi over 3. Excuse me. So your real part will be 5 halves, right? And for your imaginary part, so that will just be 5 sine of pi over 3. So that will be 5 times square root of 3 over 2. So this will be the imaginary part, and this will be the rectangular form of this polar form of complex number. So from here, we can now simplify this. Okay, so in order for us to simplify this, we have to change this square root of 13. Okay, so we have to express this square root of 13, okay, as an exponential function. Okay, so this square root of 13, we can make this as an exponential function by using this. Okay, by using these fundamentals. Okay, so as you know that e raised to ln x, it is equal to x. Okay, so your square root of 13 will serve as your x. So meaning to say, e raised to ln of square root of 13 is also equivalent to square root of 13. So we will rewrite square root of 13 this way. Okay, so from here, okay, we can also apply this law for exponents. Okay, so for terms that have same base, okay, let's say a, and if they have different exponents, okay, we can actually add their exponents. So that will be a raised to m plus n. So we can apply this here. Okay, so since we have the same base e, okay, so we can add the exponent. So that will be e raised to ln square root of 13 plus 0.98279i. So from here, this exponent, as you can see here, okay, so this exponent of e is actually a rectangular form of complex number, right? So this rectangular form of complex number, this is multiplied by this another rectangular form of complex number, right? So we can multiply this, right? So we can multiply this exponent and this, right? So we can use FOIL method in doing so. Okay, so using FOIL method to multiply this ln square root of 13 plus 0.98279i times 5 over 2 plus 5 times square root of 3 over 2i. So what will be the answer? Okay, will be 3.20619 plus 5.5532 plus 2.45698i minus 4.25561. Okay, so from this, okay, so we can simplify that. We just combine all the real part and all the imaginary part. So this will be the result. Negative 1.04942 plus 8.01025i. So from here, this is not yet the answer. Oh, so we have to simplify this further. So this is not actually an exponential form of complex number, right? Because your form in exponential form, that is actually RE theta I. Okay, but this is not RE theta I, right? So we have here this. Okay, so we have to simplify this further. And as we know, we can all apply this again. Okay, so we can separate the two exponents. So that will be e raised to negative 1.04942 times e raised to 8.01 01025i. Okay, and this value actually is a constant. So inputting this in your calculator, okay, so let's input that now in our calculator. So e raised to negative 1.04942. So that will be equal to 0.35 014. So that will be the value times e raised to 8.01025i. So this is now an exponential form of complex number, right? So this can be the answer now. Okay, so again, in our problem, it's not mentioned, okay? So it's not mentioned here what should be the final form of your final answer. So this can now be the answer. This is 0.35014 e raised to 8.01025i. So that will be the answer for sample problem number 1. Now, let's proceed to the second example. Okay, so this is z is equal to I raised to I. So these are complex numbers, right? So this is a complex number raised to a complex number. Okay, so our rule here, again, your complex number here, this I, we have to convert that into exponential form. So converting I into exponential form, we actually derive this, the value of I, in our in one of our discussions here. Okay, and we know that I is equal to e raised to pi over 2I. So we just convert this, this is in rectangular form, we just convert this to exponential form. So to solve this, you just have to solve for r. Okay, and the r that you're going to solve here will be 1. Okay, and the theta that you're going to solve here will be pi over 2. Okay, so since this will now be your exponential form, okay, your exponent here or your power here, it should be in rectangular form. But in this case, this is already in rectangular form, right? I is actually rectangular form, right? So it will be just rewritten here. Okay, so simplifying this, so we can multiply this to exponents, right? So this will just be pi over 2I times I. So that will just be pi over 2I times I squared, wherein I squared, you know that its value is negative 1. Right? So this will just be e raised to negative pi over 2. And take note that e raised to pi over 2, okay, that is actually a constant. Okay, so if you input that in your calculator, e raised to negative pi over 2, so there's actually a value. So that will be 0.200788. So this will now be the answer for this problem. Okay, so this will be the answer. Okay, so let's proceed. Now, let's talk about the logarithms of complex numbers. Okay, so for logarithms of complex numbers, we have here a natural logarithm or ln, and we have here the logarithm, okay, or log. Okay, so for natural logarithm and logarithm actually, so we just have to evaluate, okay, or in order for us to evaluate the natural logarithm of a complex number, we have to first express a complex number x plus yi in exponential form. Okay, so this complex number, okay, so this is ln of a complex number, right? A natural logarithm of a complex number. And if you actually put that in your calculator, okay, so there will be no answer, right? It will be math error even if your calculator is in complex mode. If you solve for ln of, let's say, x plus yi, you assume value for x or y, okay, so any value. So you can see there that there will be no value or it will be math error. Okay, so we cannot use calculator, okay, in solving the natural logarithm of complex number. Okay, so our rule here, okay, in order for us to solve this, we have to convert first this complex number x plus yi into exponential form. So its exponential form will be this form. Okay, and from this form, okay, it will now be ln of r times e raised to theta I. So from here, we can apply one of the laws for logarithm or natural logarithm. So as you know that the ln of a product AB, it will just be equal to ln A plus ln B. So here, we have here a product of R and e raised to theta I, right? So we can apply this law for logarithm. So this will become ln R plus ln of e raised to theta I. Okay, and also for logarithm, it will be the same. So we cannot solve this using your calculator. Okay, so that will just be math error if you solve for the logarithm of x plus yi. So instead, okay, we're going to apply this. So we have to convert first your x plus yi into exponential form. So that will be r e raised to theta I. And we're going to apply again your loss for logarithm. Okay, it is the logarithm of a product. So that will just be log of r with base b plus log of e raised to theta I with base b. Okay, so let's try to solve problems for this topic. So this will be our examples. Okay, so we have to simplify this problems. Okay, so for your number one, for the solution, okay, so that will be ln of 2 minus 11i. So if you, even if you try to input that in your calculator, ln of 2 minus 11i, okay, it will be math error. So again, we have to apply, okay, our rule here, okay, that this complex number, which is in rectangular form, we will convert this into exponential form. So this will be the exponential form. The r will be 5 times square root of 5. So again, I will no longer show you how to solve for the value of r. Okay, so I assume you already know that, okay, how to solve for the value of r of this complex number, okay, and also for the theta. Okay, so again, this complex number, it is located in the second, in the fourth quadrant, right? So this will be its theta or argument. That will be negative 1.39094i. So this will now be the exponential form of this complex number. Okay, so from here, we can now apply, okay, the law for logarithm, which is the natural logarithm of a product. So this is a product of 5 and 5 times square root of 5 and e raised to negative 1.39094i. So we can apply this. So applying this, so this will become ln of 5 times square root of 5 plus ln ng e raised to negative 1.39094i. So from here, okay, we can actually simplify this. We know that ln of 5 times square root of 5, we have a value for that. So inputting that in your calculator, that is ln of 5 times square root of 5, that will be 2.4116. Okay, and for your ln e raised to negative 1.39094i, we can apply this rule for logarithm. Okay, so we can apply this rule. Okay, that if you have ln and you have a raised to n, you have power here. Okay, so you can actually put down, okay, that power, okay, beside ln. So this can be bring down here. So that will become n of or n times ln of a. So here we can also bring down this power negative 1.39094i. We can bring that down here, okay, beside ln. And what will remain here is ln e. And as we know, okay, that the value of ln e is actually 1. So even if you check that in your calculator, the ln of e is actually 1. Okay, so what will remain here is just negative 1.39094i. So this will actually be the answer for this. Okay, this is the equivalent of ln of 2 minus 11i. Okay, now let's proceed to the second example. So for our second example, this is log of 5 minus 7i with base 4. Okay, so we will also apply what we have done here in our example number 1. So this complex number in rectangular form, we will convert this into exponential form. So this will be our exponential form for this rectangular form. So our r here is square root of 74, and our argument will be negative 0.95055. That will radian. No? So that will be our argument. Now we will again apply one of the laws for logarithm. Okay, so this will be logarithm of a product. So the product we have here is square root of 74 and e raised to negative 0.95055i. So applying this, okay, so this will be log of square root of 74 with base 4 plus log of e raised to negative 0.95055i with base 4. Okay. So simplifying this, as we know, okay, inputting this in your calculator, this is log. Okay, this is log of square root of 74 with base 4. Okay, so the answer for this will be 1.55236. Now, for the value of this, okay, so we can also apply here that this exponent, this power, we can bring this down. Okay, so we can bring this down. So we can bring down negative 0.95055i, okay, beside the log of e with base 4. And as we know, the value of log of e, okay, let's input that in our calculator. This is not 1 ha, log of e base 4, this is not 1. So there's a value for this. So let's input this in our calculator. Log of e raised to or with base 4. So that is actually 0.72138. Okay, but we're going to multiply that further, okay, by negative 0.95055i. So the answer will be negative 0.68 568i, okay, for that term, no? So again, that is log of e with base 4 times 0.95055i. So that will be negative 0.68568i. So this will be the answer, 1.55236 minus 0.68568i. So this will now be the answer for this problem. Okay, so now let's proceed to sample problem number 3. So this will be the third example. This is ln of I. Right? So we have to convert I into exponential form, and its exponential form is e raised to pi over 2i. Okay, so from here, okay, we can now apply the rule for logarithm or natural logarithm that ln e raised to pi over 2i is equal to ln of 1 plus ln of e raised to pi over 2i. So our r here is actually 1, right? So that's why it's 1 here. Okay, so simplifying this further, as we know, the value of ln1 is 0. Even if you input that in your calculator, the value of ln1 is 0. So that will be 0. Now, for ln of e raised to pi over 2i, we can put pi over 2i. We can bring that down right beside ln e. And we know that ln e is 1. So the value for this will just be pi over 2i. So that will be the value of ln I. It is equivalent to pi over 2i. Now for number 4, this is ln of negative 3. So for ln of negative 3, so if you input that in your calculator, that is actually math error. So we cannot solve this using your calculator. So we can solve this by applying our concept here. This negative 3, okay, we're going to convert this into its equivalent exponential form. So to solve for its exponential form, this is actually in rectangular form, right, with zero imaginary part. So this is just a real part, no? But this is a rectangular form of complex number. So to solve for its r, that will just be square root of negative 3 squared plus 1. Okay, so that will be square root of negative 3 squared plus 1 squared, right? So that will just be, no, hindi pala 1. So that is not 1. So that will be 0 pala. So square root of negative 3 squared plus 0 squared. Since your imaginary part is 0. So that will be 3. Okay, so your r will be 3 and your theta. Okay, so if you're going to graph your negative 3, okay, if you're going to graph that in your Argand diagram, it's actually located in the negative x-axis, right? Since this is negative 3, okay, and your x-axis is the real part, okay, of your complex number. So it is located in the negative x-axis, right? So if it's located in the negative x-axis, its theta, okay, its argument from the reference positive x-axis, it will be pi. right? That's why its argument here is 5. Okay, so from that, okay, we can apply our concept here. Okay, it will just be ln of 3 plus ln of e raised to pi I, wherein your ln 3, we have a value for that. The ln of 3 is 1.09, okay, 861. Okay, while this term, okay, it will just be brought down. Your pi I will be put down beside your LNE, so that will be pi I, and LNE, as you know, is 1. Okay, so that would be the value for this. So this is 1.09861 plus pi I. So that will be the answer. Now for number 5, it's actually be the same, okay, as what you have done here in your number 4. Okay, so again, you have to convert your this complex number. Okay, so this is in rectangular form. You convert that into its equivalent exponential form. So this will be the exponential form. And from that, you can apply this, that log 3 times e raised to pi I is also equivalent to log of 3 plus log of e raised to pi I. So from that, okay, we can simplify this. We know that the log of 3 is 0.47712. And the log of, so pi I can be put down beside log, right? So pi I times log e. So that will be pi times log of e. So the answer for that will be 1.36438 I. So this will now be the answer for number 5. So that concludes this discussion. I hope you learned from this topic. So don't forget that you will have a course material assessment task for this topic. So your CM assessment task number 1.2 is located in your course material, okay, uploaded in the files in Teams. Okay, so keep safe, class. God bless. Bye-bye.